Now we're going to change things up here for question C because I want to do this with an algebraic method. I want you to understand how to do it with an algebraic method. You're going to have to do that on your exit ticket. So since we just did the previous problem with a graph, let's see if we can figure out what's going on with 23 degrees. In other words, does the ball go far enough and high enough with a 23-degree angle? Now remember, it's a home run when the ball travels 400 feet. So that's what we're going to start with. We're going to plug 400 feet in for what? In for x, in for y, or in for t? Well, it's not for t because t is time. And it's not for y because y is a vertical distance. That's right. We're going to plug 400 in for x. So we plug 400 in for x. Of course, you may notice that we already have 23 degrees in place of theta. But yeah, if you take a careful look at this, you actually have an equation that you can solve for t. Now, understand what's happening here. Yes, we're going to divide both sides by 146 times the cosine of theta. That's something you can try on your calculator. But understand what's happening here is we're getting the time when the ball travels 400 feet, right? It's the time that matches with 400 feet. Okay, if you do that division, you end up with 2.96. Let's call that 2.96 seconds just to make sure that we're clear. Now, again, in 2.96 seconds, that ball is going to travel 400 feet horizontally. So do you think I can use 2.96 seconds to figure out how high the ball goes? Yes, I can plug in 2.96 into my vertical equation. And if you look carefully at that vertical equation, the only thing that's missing is the time. Now, I would say this is something that you're going to want to actually try on your calculator. Don't just watch me do it, because sometimes students wonder what mode their calculator should be in. Okay, well, your calculator should be in degree mode, but on your home screen, you're just going to type in this formula. So if your calculator is in degree mode, type this in on your home screen, and you should end up with 32 point approximately 45. Now remember, that's actually the y value. So that's the height. And so is it a home run? Is it a home run? Does the ball actually get high enough? Remember, the home run fence is only 10 feet high. So at 400 feet, the ball's 32 feet high. That thing's going to be a nice home run. Even though we weren't supposed to solve this problem with a graph, we can still use the graph to understand, again, everything that's going on in this problem. So we have the horizontal component, which is what we started with. We kind of forced it to be 400. Of course, at 400, we discovered that the time is 296. And look what that height is. Look at that height. It is the y value. It's that 32 number. And again, the home run fence is closer to here, 10 feet. So the ball is definitely high enough to clear. Somebody's going to catch that and have a souvenir. Now, number 59D, it says to find the minimum angle required for the hit to be a home run. I'm going to be honest with you, this is a little bit more of a challenging problem, but I'm going to be looking that you definitely follow along. And the reason that I want to expose you to this kind of problem is so you can continue to get the idea of the separation of x and y. You see, for this problem, it's still true that the home run fence is 400 feet in the horizontal. So to plug in 400 would be smart. Now, what we discover quickly is that we don't have, or excuse me, we do have too many variables. I mean, we have two variables, so I'm going to need a second equation to go along with this. And that, of course, would be your y equation. Now, I know something about the y value, or the height of that home run fence. In a similar fashion, I can plug that number in. Of course, it's 10, and we can plug that in for y. Just like I noticed before, I have an equation with two variables. But actually, what I now have technically are two equations with two variables. And what are two equations with two variables? Well, that's right, a system. Okay, this is just quite a bit more advanced system, but nonetheless, it's a system of equations. And so now I've got to kind of feel like I'm going to perhaps do some kind of substitution method. Yeah, I think we can do a substitution method if we solve this first component for t. Do you see that if you solve that for t, you're basically going to divide both sides by 146 cosine of theta. 400 divided by 146 comes out to be about 272. And of course, I'm dividing both sides by cosine, so I still have the cosine in the denominator. Now, if I solve the first equation for t, I'm doing that so that I can then substitute that into the second equation. See what happens when we substitute it in. Looks like we're going to get some pretty fun math here. Why is it fun? Look what happens when sine of theta meets 2.72 over the cosine of theta. In other words, I have sine over cosine. Here, let's finish plugging in, because we get a little bit of fun here too. We're going to plug in 272 over cosine for t squared. Now, when you simplify the numbers in this problem, it is 146 times 272. Might as well multiply those together. You're going to get a familiar number. And what were we saying here? Yeah, we end up with sine over cosine. Let's get some new values. 146 times 60 times 2.72. Yep, that goes back to 400. Sine over cosine, you got it. That's a tangent. Now over here, I wish I could tell you that something really cool happens. 16 times 272 squared, I guess at least we can multiply those together. So again, 16 times 272 squared is about 118. How about that cosine squared in the denominator? Isn't that like 1 over cosine squared? And, oh yeah, that's equal to secant squared. Now, we did some, of course, some fancy things here, but if you just sit back a second and look at what we've got, we now finally have an equation with just one variable. And, oh my gosh, look what variable it is. It's theta. I think we were trying to find theta. I think we were trying to find like the minimum theta. So we're getting pretty close. Now, how are you going to solve this equation for theta? Well, you're not going to be able to solve it with algebra, just to be upfront and frank. But when you can't solve something with algebra, you can resort to a graphing method. And basically a graphing method says that if you make the equation equal 0, then if you proceed to type this equation into your calculator, well, maybe we'll see something. Like maybe we'll be able to see when the equation is equal to 0. And just keep in mind that what we're really finding is the theta when the equation is equal to 0. Now, when it's time to graph this equation, you have to realize that we're back to just graphing like a regular function. You have to change your mode back to function mode. And you're really going to just type the equation into the regular y equals screen. You're not going to have a theta because it's just a variable, so the calculator treats that like an x. But since x is the same as theta, you're going to have to make your window kind of match with that idea. What idea? Well, basically that x would go from 0 to 90 because, once again, x is theta. So it's kind of like you're only looking for 90 degrees worth of possible thetas. Now, the y window gets a little tricky here because you really don't know what that is until you kind of experiment and I'm just telling you that this will be sufficient for us to be able to see the graph. When you graph the equation, you get this kind of strange looking shape. Understand, this is not the flight of the baseball. This is actually just different thetas that will make the equation true. Okay, but we're looking for the smallest thetas that make the equation true. Okay, so here the equation is true because it's equal to 0, and here the equation is true because it's equal to 0. So if we use the trace button or maybe even the 0 command, left bound, right bound, we end up getting an x value, which remember is the same as theta, of about 19.27 degrees. Now that would be the smallest angle that you have to launch the baseball, that you have to hit the baseball in order for it to travel what? To travel 400 feet and also get a height of 10. Interesting, there's one thing that we don't really know, and that's how much time this would take, but it wouldn't be too hard to find that time, because if you remember, we had an equation that said that time is equal to 272 over the cosine of theta. If we really wanted to, we could plug 19 degrees back in here, and we could also find the time that that's going to take. Now, just a friendly, gentle thought here. You're going to want to put your calculator back into parametric mode, assuming that you followed along, so that when you do the exit question, which will not be quite as hard as the letter D, but that way when you do the exit question, your calculator is kind of set back up for you. And you'll show a graphing method on the front, and then you're going to show an algebraic method on the back.